Welcome to the Make It Make Sense podcast, where we do deep dives into everything interesting.
Hey everyone, and welcome to another deep dive. We're diving headfirst into the world of quantum computers today.
Which is a world that feels like it's straight out of sci-fi, but researchers are making huge strides.
Absolutely. And today, we're zeroing in on a critical piece of the puzzle, quantum error correction.
It's the key to unlocking the power of these incredible machines, and we're looking at two landmark papers.
One from 2021, and get this, another all the way back in 1995. We're going back in time to see just how far we've come.
It's fascinating to see how these ideas have evolved, and it all begins by grasping just how fragile quantum information can be.
Right, and that's where our 2021 paper comes in, introducing something called the Gottesman-Kiddew-Preskal code.
Or, as we like to call it, the GKP code.
Catchy, right? But in all seriousness, this GKP code is all about protecting quantum information, keeping those qubits in line.
Exactly. It's like, imagine storing data on something that's constantly vibrating. That's essentially what we're doing here. But on a scale that's mind-bogglingly small, thousands of times smaller than a human hair.
Okay, my mind is already a little blown. But how do we use these tiny vibrations to actually store information?
Now that's where things get really interesting. The GKP code uses these fascinating concepts called squeezed states and superpositions. It's like we're taking the uncertainty that's just inherent in the quantum world and actually using it to our advantage.
I've heard of superposition, that whole thing where a particle can be in multiple states at once, right? But squeezed states, that's a new one. What does it mean to squeeze a quantum state?
Think of it like squeezing a balloon. You're pushing the air into a different shape. In a similar way, we squeeze the uncertainty of a quantum state. We're making it more defined in one aspect, even if it gets a little fuzzier in another.
So it's like focusing that uncertainty instead of letting it be this big blur, which helps make the information clearer.
Exactly. It's all about strategically managing that uncertainty. And now, let's bring it back to those vibrating objects and the GKP code. Imagine those vibrations as ripples on a pond. The GKP code arranges these ripples in very specific patterns, and each pattern represents a different piece of information. And by squeezing certain properties of these vibrations, we can make those patterns much more distinct and less prone to errors.
Okay, so instead of just random ripples, we have these carefully organized patterns, and the squeezing helps keep them from getting messed up.
You got it. And that's the elegance of the GKP code. We're creating a language for quantum computers using the very principles that govern the quantum world.
It's amazing to think that these incredibly complex concepts could hold the key to a whole new era of computing.
Absolutely. But as with anything new, there are always challenges, and in the quantum world, errors are a big one. How do we keep those carefully crafted ripples from being disturbed by the chaotic nature of the quantum realm?
That's the million-dollar question, right? And that's exactly what we're going to uncover as we explore the different types of quantum errors and how the GKP code tackles them head-on after a quick break. So we've got this picture of information stored in these tiny vibrating objects like ripples on a pond.
It's a powerful image, right?
It is. But the quantum world, it's not exactly known for being calm and stable.
Definitely not. It's more like trying to draw a picture in the sand on a really windy day. The environment's always trying to mess things up.
So how do we make sure those ripples don't just disappear? What kind of errors are we up against here?
Well, one of the biggest challenges is actually called loss, which is kind of what it sounds like.
Like those ripples on the pond, they just fade away.
Exactly. The information leaks out of our carefully controlled system.
And what causes that? Where does that information go?
It comes down to how these quantum systems interact with their surroundings. Even the tiniest interaction can steal away some of that information. Think of a single photon, a particle of light, bumping into our vibrating object and changing its rhythm just slightly. Those little disruptions add up.
It's such a delicate system. Are there any other ways these errors can pop up?
Oh, absolutely. Another big one is heating. Remember, our information's encoded in those specific vibrations.
Right, those carefully arranged ripples.
Exactly. But if that object gets too energized, it starts vibrating more erratically.
Like it's getting overheated.
Precisely. And those ripples, those patterns that hold the information, they get all jumbled up.
Not good for our data.
Not good at all. And then we have dephasing to worry about too. Imagine a choir where everyone starts in sync, but as the song goes on, they drift out of harmony.
Okay, I can picture that.
That's kind of what happens with dephasing. the different parts of our quantum system, they lose that synchronization and the information gets scrambled.
It's like quantum information is under constant attack from all sides.
In a way, it is. It's a constant battle against these errors.
So how do we even begin to build a reliable quantum computer with all of this going on?
That's where the true brilliance of this GKP code comes in. It's not just about encoding information, but doing it in a way that lets us detect and correct these errors. It's like we're giving our quantum computer a set of tools to fight back.
Okay, so it's like a safety net, catching those errors before they cause too much trouble.
Exactly. And it does this by using those squeezed states and superpositions we were talking about earlier. They're crucial for creating this more resilient way of representing information in the quantum world.
So it's like building a fortress around our data using the very laws of quantum mechanics.
That's a great way to put it. But of course, it's one thing to design these codes and another thing entirely to actually implement them in a real quantum computer.
Right, because we're talking about controlling these incredibly tiny objects and making them behave exactly how we want.
And that's not easy. The 2021 paper really dives into the nitty-gritty of these challenges.
Which is what we love to do here on the Deep Dives, get into the details. So what are some of the big roadblocks researchers are facing as they try to bring this technology to life? What's standing between us and this more stable quantum future? It really does feel like we're trying to build something incredibly intricate and delicate here, all on this tiny scale.
It's a huge challenge for sure. Kind of like we have the blueprints for a magnificent skyscraper, but haven't quite figured out how to pour the concrete yet.
And all while trying to use tweezers the size of atoms.
Exactly. And one of the biggest hurdles is that those squeezed states, those carefully crafted patterns of ripples we're relying on, actually creating and controlling them in a real system is, well, it's incredibly difficult. We're talking about controlling objects at the atomic level here, isolating them from any kind of environmental noise, and then making sure they interact with each other in just the right way, exactly how our theories predict they should. It requires some truly cutting-edge experimental techniques.
Pushing the very boundaries of what's even possible. The 2021 paper, it mentions these things called bias noise qubits. What are those? They sound interesting.
Yeah, it's an exciting area of research. So not all qubits are made equal, right? Some are just naturally more resistant to certain types of errors, just like some materials are stronger than others, some qubits are better at holding on to their information. And these bias noise qubits, they're designed to be less susceptible to specific types of errors.
Like they have a built-in defense system. That's pretty cool.
Exactly. Researchers are exploring all sorts of different materials and architectures, trying to figure out how to create these more robust qubits.
It's a hot topic in the field right now.
So we're trying to build our fortress out of the strongest materials possible. But even with those, it seems like there would still be limits. Is there any way to push those limits even further to make these error correction capabilities even stronger? There is. And that's where this idea of concatenation comes in. The 2021 paper talks about combining the GKP code with other error correction techniques.
Concatenation.
No.
Okay, that sounds like we're about to get really serious about protecting our data.
We are. Think of it like this. We're building multiple layers of protection around our information. So the GKP code might be one layer, and then we add additional layers using other error correction codes, each one designed to deal with different types of errors.
So it's like a multi-layered defense system. Like we're not just relying on one lock on the door, but we've got an alarm system and maybe some guard dogs too, just in case.
That's the idea. We're creating this system that's resilient at multiple levels. And the beauty of it is that these different codes, they can work together. Each one makes up for the weaknesses of the others, so they complement each other.
Like a team of specialists, all with their own area of expertise, coming together to solve a really tough problem. The paper mentions something called the surface code. Well, what's so special about that one?
The surface code is a great example, and it's a popular choice for this concatenation process because it's really good at dealing with errors that are localized, kind of contained to one area. Imagine a grid of qubits, each one connected to its neighbors. Now, if an error pops up in one of those qubits, the surface code can quickly identify it and correct it by looking at what's happening in the qubits around it.
So it's like a network of sensors, constantly monitoring for any disturbances and then jumping in to fix them before they spread.
Exactly. But as with anything in quantum computing, there are always trade-offs. So while concatenation can dramatically improve our error correction, it also makes things more complex. We need more qubits, more control systems, and more computational overhead to make it all work.
It's always a balancing act, isn't it? Robustness versus efficiency.
Always. And finding that sweet spot where we can have both, that's a huge part of what researchers are trying to do. But honestly, when we look back at how far we've come, Even in just the past few decades, it's mind-blowing.
It really is. Thinking back to that 1995 paper, the one that introduced Shor's algorithm, it's amazing to see how much progress has been made since then.
Totally. Back then, building a quantum computer, it seemed almost impossible. But now, with every new discovery, every breakthrough in error correction, we're getting closer. And the GKP code and these concatenation techniques, they're a big part of that.
It really is a testament to human ingenuity. Who would have thought we'd be talking about storing information in the ripples of tiny vibrating objects?
Right. And the thing is, this is just the beginning. Quantum computers have the potential to revolutionize so many fields: medicine, material science, artificial intelligence, you name it. And the work being done on quantum error correction, it's paving the way for a future we can only begin to imagine.
It's been an amazing journey exploring this world with you today. It makes you wonder what other seemingly impossible challenges are out there, just waiting for us to unlock the solutions. Thanks for joining us for another deep dive. We'll see you next time.
Thanks for listening to another episode of the Make It Make Sense podcast. As always, if you learned anything from this episode, please take a moment to like this video, or if you found it intriguing and want to hear more, consider subscribing.